The basic idea of any machine learning method is quite simple. Given a model or hypothesis space, find or learn a hypothesis that best predicts the label of any data point. The prediction of the label must be computed solely from the features of the data point. To implement this machine learning principle, we need some means of assessing the quality of a hypothesis and, in turn, a way to compare two alternative hypotheses. Consider the prediction for a data point characterized by a numeric feature x and a numeric label y. Let's assume the true label of the data point is y equal 2. But the predicted label value is different. A loss function is a quantitative measure for the prediction error incurred by a hypothesis. In its most general form, a loss function is an assignment of a real number, typically non-negative, to a pair consisting of a data point and a hypothesis. The data point is characterized by features x and a true label y. We apply the hypothesis to the features of the data point to obtain a prediction y hat for its label. The value of the loss function is a measure for how well the hypothesis predicts the label. This concept of a loss function might seem quite abstract at first. Let us build some intuition for the use or for how to use loss functions by considering some specific examples. Maybe the most widely used loss function for numeric label values is the squared error loss. This loss is defined as the square of the difference between the predicted label value and the true label value of a data point. Note that we can evaluate the squared error loss only if we know the true label value of a data point. Such data points are referred to as labeled. Another example for a loss function is the absolute error loss. As for the squared error loss, the absolute error loss can only be used for data points with numeric label values. Note also that, as for the squared error loss, we need to know the true label value y of a data point to evaluate the absolute error loss. The squared error and absolute error loss can only be applied to numeric label values. Let us now consider loss functions for classification problems where the label values represent one of finite categories. For example, the label might indicate if an image shows a cat or a dog. Classification methods learn a hypothesis map that reads in the features of an image, for example the pixel intensities, and output a predicted label value which is either cat or dog. We could then define a loss function by defining or specifying a loss value for each possible combination of true label value and the predicted label value. It is often useful in classification problems to learn a real valued hypothesis map, even there are only finite different label values corresponding to the different categories. As a case in point, consider a binary classification problem with data points having labels being either -1 or +1. We can then learn a real valued hypothesis that is used to predict the label via its sign. In particular, if the hypothesis delivers a positive value, we predict the label is equal to 1. Otherwise, we predict the label is equal to -1. Besides the sign of the hypothesis, we can also use its magnitude as a measure for the confidence in our predicted label value. We can visualize the behavior of a loss function here by plotting the loss value as a function of the hypothesis map, evaluated for the features of a given data point. Here we consider the loss obtained for a fixed data point whose true label value y is equal to 1. The correct classifications correspond to the right half space, whereas the wrong classifications are located in the left half space. The more confident we are in a classification, the further away we are from the origin or from the vertical axis here. A useful loss function here should decrease, should have smaller values towards the right, as this direction corresponds to increasing confidence in correct classifications, and this is what we would like to favor. In the other direction, towards the left, the loss function should increase and take on larger values, as this direction means an increasing confidence in a wrong classification, which is exactly what we would like to punish such a situation. One example for a loss function that has the desired behavior is the logistic loss, which is also known as the cross-entropy loss. You can see here the formula for the logistic loss, which applies only if the label values are 1 and -1. However, we can use the logistic loss for any binary classification problem by appropriately encoding the two categories using the label values 1 and -1. Note that the logistic loss is a smooth or differentiable and convex function of the hypothesis value h of x. Another widely used loss function for binary classification is the hinge loss. Note that, like the logistic loss, it is a convex function of the hypothesis value. However, in contrast to the logistic loss, the hinge loss is not differentiable everywhere. Maybe the most intuitive loss function for binary classification is the 0-1 loss, which is either 1 if the predicted label is incorrect or wrong, or the loss value is 0 if the predicted label value coincides with the true label value of a data point. Note that the 0-1 loss is neither convex nor differentiable when viewed as a function of the hypothesis value h of x. Like the data and the model, also the loss used by a machine learning method is a design choice for the machine learning engineer. Again, as for data and model, there are at least 3 design aspects for this choice. These aspects are the statistical and computational properties, as well as the trustworthiness of the resulting machine learning method. Computationally, machine learning methods are optimization algorithms that aim at learning a hypothesis with minimum loss. It turns out that loss functions that are differentiable or smooth and convex can be minimized quite efficiently using simple gradient descent methods. 2 examples for a smooth and convex loss function are the squared error loss for regression and the logistic loss for classification problems. Statistically, we want the resulting machine learning method to be not too sensitive to a small number of outliers whose label values are erroneously large. Here we would like a loss function to tolerate large prediction errors for a few outliers. This suggests in turn to prefer the absolute error loss over the squared error loss. Indeed, the absolute error loss increases only linearly with the magnitude of the prediction error instead of the quadratic growth by the squared error loss. Beside the computational and statistical aspects for choosing a loss function, we must also take into account the trustworthiness of the resulting machine learning method. While it is difficult to grasp the meaning of specific values of the logistic loss, reporting the average 0-1 loss of a hypothesis can be easily interpreted as an error rate. It is also common practice to communicate the quality of a classification method by reporting its accuracy on a test set. Note that the accuracy is a trivial rescaling of the average 0-1 loss.